Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, everyone. Welcome back to another exciting edition of IT Pro TV. I'm your host, Vaughn Smith, and this is our Cisco Cloud Fundamentals series. And this episode, we're going to take a look at ACI basics as part of our cloud networking section or topic area. And here is the one and only, the most amazing person in the world, Mr. Ronnie Wong. How are you?
I was looking around the room, Vaughn. I was starting not to go like she's introducing the wrong person here. Yes, it is me. I am glad that you're back, and I'm also glad that you're joining us as we continue on in our Cisco Cloud Fundamentals. And we are taking a look, of course, at the idea of ACI basics is what we're actually picking up on this episode. But before we move into the realm of ACI, that idea of the application-centric infrastructure, I need to backtrack just a little bit because I realized something from the previous episode, which is I forgot an exam objective, okay, just briefly, where I need to make sure I cover this topic because it may be exam testable material, and I don't want you to go, hey, he skipped this one topic. He must, not want to do it. No, I did want to do it, but just like everything else, I keep talking, and then all of a sudden I realize I forgot it. So we're adding it in here in the beginning of the episode. So Vaughn, before we head into ACI basics, we'll actually need to take a look at the idea here as we continue on about talking about SDN just a little bit. Okay, so that's what we did in the previous episode. We talked about software-defined networking and the way that it ends up working. So Vaughn, with a regular switch and a regular router, okay, and the way that things end up working, okay, as data moves through those physical devices, well, remember that data goes into a port. Well, how does it know what port to leave, okay? And when it does something like that, that means that there's some logic, there's something working in the background to ensure that it gets to go where it needs to go. Now, Vaughn, if all this process actually happened on one particular layer, it would actually be a long time before data actually would get to move, across a particular device, right? The reason why is that as a packet moves in, it would have to stop. It would have to do the processing that it needs to, okay? And then when the processing is over, then it would have to actually say, all right, I know now where this is going. And at the same time, other processes are handling, are actually moving and different things are going on. And then we could actually forward that data along. Well, Vaughn, the problem that we have in terms of routers and switches is simple. Vaughn, you may actually have a packet that's actually coming in, well, in both interfaces, or let's say all three interfaces here, and all that still has to happen and do that just about simultaneously. If it's a switch, you can have multiple devices communicating, well, with a bunch of other devices on the, in that switch as well, because the switches connect port to port. So how does this work efficiently? How does it actually end up working here? Well, let me show you an example using a router diagram that will help us out. Now, I've drawn the simplest router possible, and let me zoom in so that we can see this. So, Vaughn, on the top of my particular screen here, okay, or kind of midway on the screen, I've drawn a rectangle, excuse me, and what I show you is that there's three interfaces. There's GI or gigabit 0/0, there's 0/1, and then another one up here, which we'll say is gigabit 1/0. So that's a typical router that has three interfaces on it. Well, the way that this ends up working for us, Vaughn, is that as data moves through, as it comes into the interface, it gets put onto what we call the data plane itself. But remember that data that's going through router is actually designed to go from what? One network to another network, right? And we find all that information out inside of the header. So as data actually moves on to the data plane, what it does to actually figure out which of these two interfaces to go out of, it has to hit what we call the control plane. The control plane for us is where it makes decisions. So one of the easiest ways to think about this idea of the separation that we're talking about here, okay, is that it differentiates the idea here of some of the things here, okay? So the control plane for us is all about trying to say, hey, what do I need to do to this packet to get it where it needs to go? And the data plane is saying, okay, I'll move the packet to where it needs to exit, okay, is what happens. So to make this much more efficient, we don't process a lot on the data plane. That is just a plane to move the data as quickly as possible through this device. So Vaughn, if this packet is coming in for another network, that means it's off of one of these two interfaces over here. Well, it is when it comes in, it takes a look at the header information, and then it takes a look and it sends it up here in terms of the header information. that then takes a look at different routing protocols that it may be attached to, take a look at the routing table and figure out where it's going. And once it realizes where it's going, it then puts it back onto the data plane, allows it to actually work much more efficiently. Now, this is also done not just at the CPU layer, okay, but with all of our routers and switches today, it's done at the ASIC layer, okay, the application-specific integrated circuitry. So it can happen on the interface itself, which makes it lightning fast, is what we want to be able to do, okay? So by being able to understand that separation and how this is done, because this is all done in software, Vaughn, okay, in the way that this ends up working. Now, on the ASICs, it's essentially software that's actually embedded into the hardware itself, and that's what makes it super fast. But now when we move into the realm of SDM, essentially, or SDN, excuse me, N as in networking, right? When we move into that realm, all this actually changes just a little bit more. So let me zoom out and come back over here, okay? So in software-defined networking, we don't have physical devices in terms of what you and I access and what you and I configure, okay? It may all be cabled together, okay? All the stuff that we need to is cabled together, but when we actually send data in, instead, we actually get access to what we call the SDN controller. Now, the SDN controller, it does kind of the same thing, but it does it just a little bit differently here, okay? It actually combines back together the control plane and the data plane together, essentially in this virtualized layer, identifies events and patterns, and then when it realizes that, what it does is it spreads it across the entire topology of the cloud, saying, hey, this is where this packet is going. And why does this make it efficient? Because it means it doesn't have to stop at every virtualized device along the way to figure out where things are going. Does that make sense, Vaughn?
Yeah, it's almost like a traffic controller for an airport or whatever.
Yeah.
I'm finding where you're coming in from, and then I'm going to go around and just kind of tell you where to go.
Yeah, so essentially, it's actually kind of neat. And I like your airport analogy. I was trying to think of what it says. Because of the updating that happens, right? So, Vaughn, I know that you've actually been on planes a lot more than I have. Even in the past year, you've probably been on plane more than I've ever been in my lifetime. And I'm not criticizing it, but you've been in enough airports to know that all the screens that you look at for departures and arrivals and stuff, well, when it updates in one place, it updates every place, okay? SDN essentially is doing the same thing. Once a new packet comes into the SDN controller, okay, it doesn't just say, okay, for this device, for this particular controller, we're going to update it. It takes a look across the entire topology, and if there's another SDN controller, it says what? Oh, this essentially is where it's going if it has to. So that means if data comes in from the other side, it actually already knows how to get there. So that's why it makes it much more efficient. But if we do physical switches, right, it has to kind of go through here, this router, and then goes to the next divider, and it has to do the same process over. But SDN says if I configure it here, I can spread that through the entire topology, and everybody knows the exact same thing.
Yeah, like it's going to update on my phone, my Delta or whatever airline I'm traveling, the app, and then the board, and the whole nine, and then they usually announce it later, you know?
Right, yeah, that is delayed. And
yeah. The
so,
actual person gets on the horn, but...
Yeah, sorry, you're moving to gate 4, A4.
Yeah.
I'm at D99.
Better start running.
Yeah, you better start running, yeah, so you can see stuff like that. But that's kind of the neat thing about this, right? SDN also doesn't require then the underlying infrastructure to be reconfigured to make the networking work, okay? So we, again, with the cloud, remember that this is an access type of model, right? That when we start talking about cloud computing, it's an access type of model that gives us this ability to do so without having to reconfigure devices to connect them together again. It actually allows us that software abstraction to do all this, and that's where the SDN comes in. So just another portion of something that you may want to at least understand and hook into as you actually move on, as we move into the realm of ACI. So Vaughn, that was just a little bit that I wanted to make sure that we understood before we moved on here, okay? Now, Vaughn, as we move into the realm of the ACI as well, okay? This stands for Application-Centric Infrastructure. This is kind of weird because of the way that people describe ACI. So there's a lot of people that say, well, ACI is essentially a subset of software-defined networking. And it may be, okay, so for all that I know. But at least the way that I understand it, and the technology that's actually there, is that software-defined networking at the very beginning, though, was really more about automation and getting things to speed up in the process, or not having to reconfigure, not having to actually go in and configure, but to actually rely more on programming in that sense, right? But really, it's about the process of speeding things up and getting automation running doing stuff like that. ACI can do not only those things, but it can also, a lot of times here, not have to worry about what devices it has to configure. So that means it doesn't matter whether it's a switch or firewall or router. We can take one interface and be able to configure them all and do everything. And that is done through the application-centric infrastructure. It's saying that we're going to manage these devices or something like the devices, the virtualized devices, through software. And it's actually going to work for us in the way that we need to. So in that sense, it's a newer approach than the idea of SDN. Okay? SDN was really kind of a new thought pattern, right? That we don't go in and we configure everything line by line, but we can actually issue commands, run it through the SDN, and the SDN can push those commands out for us through the orchestrator and make everything work. So in ACI, though, we need to understand that this, again, is that newer approach, and it essentially solves some of the issues that SDN cannot actually solve by itself. So when we start to think about it, what are some of those challenges that SDN had that ACI ends up solving? Well, one of the big challenges that they had is when we talked about it with SDN, that we talked about the idea of open flow, that this is an open standard that is about southbound interfaces and the idea of the southbound type of communications, that there were certain limitations with that in terms of scalability. So once you got to a certain point, it didn't scale as well as we wanted to. Well, ACI actually helps us there too, okay? Because instead of actually having to rely on that SDN type of structure where it might be great for things like certain devices, but not great for things like other devices here, well, then ACI says, no, we're actually kind of describing how things are to be done. In other words, it's more of a declaration than it is a prescription of exactly how you're supposed to configure everything. So you're actually sending things a little bit differently. Also, managing flow tables too, okay? Now, flow tables are just like what we described here. How does data move east and west across our network? Well, ACI also helps us by making sure that we can manage flow tables inside of a very complex structure. SDI, it knows how to actually do some of the programming, but it can't actually manage the actual flow between east and west traffic very well. I'm not saying it can't do it, but not as well as what ACI can do. And then, of course, OpenFlow itself, it actually only works well when the entire SDN infrastructure itself and the controller has full awareness of all of the devices, networking devices' state, to make sure that it can actually manage every part of whatever device is doing. So some devices may not communicate fully, okay? In other words, they may not actually allow you to do certain things, but some devices allows you to actually control it fully by what you also needed to. So normally the SDN, and this is kind of the wording that I kind of messed up, I called it a prescriptive model. Technically, it's what they call an imperative model itself, which states, here's how things are supposed to be configured. Well, the SDN, though, is more of a declarative model that says, Vaughn, I need you to do this, okay? So instead, and we call it micromanagement, right? In the human world, Vaughn, the idea is SDN is a pretty good micromanager, okay? Now, Vaughn, do you like being micromanaged?
Not
Probably
really.
not. Yeah, probably not. And don't
I'm
get
not
me
sure
wrong.
many people
Yeah.
are.
Well, I mean, it works well in some instances, right?
Yes.
Okay. So at the very beginning, when we don't know how to do things, we can actually do that and micromanage a little bit more, and then you kind of let go and let them fly.
Well, almost like talking about airports. You probably need to manage like where everybody is at, and because everybody needs to be in their place, and make sure that we have the ticket people and the baggage people. So yeah, you might want to be micromanaged there to
Yeah.
run efficiently because it's a really large operation.
Yeah. So once you actually start doing stuff like that, there are certain things that it's great at. But the way that ACI works, it says, no, let's just do this. We'll tell those devices what we expect to be done, and we'll allow those devices with an agent to actually be able to do those. Okay? So that's what they'll do. They'll configure it for us, and we'll do that. The other challenge that we have inside of SDN, since it's essentially software-defined networking, is that SDN relies heavily on overlays. Well, remember that, at least in a thought pattern, right? All of cloud computing essentially is an overlay. You and I never get to peek under the hood and try and figure out how all these devices are connected together. So, Vaughn, it's like the first time you don't know anything about engines on cars, right? You can say, yes, something is wrong. Well, how do you know? Because something's clicking underneath the hood. Well, most of us, me, let's put it that way, I would like to lift up the hood and see what's going on. But in cloud computing, it doesn't do that. It just says, no, you don't have to worry about that. We've taken care of all that underneath here, and all you have to do is rely on what we've given you access to, and it should work. Okay. Well, that reliance on that in the SDN model is that's what we call the idea of software-based overlays. Okay. And even though that can actually work for us in the SDN to a point, it doesn't work well with a lot of management tools that require visibility into the underlying network infrastructure. So if it can't control those devices, it just says, okay, I can see stuff. Now the SDN can kind of mimic and report some of the stuff back, but it may not give us true visibility in. Okay. Also, remember that overlays are also vendor specific. So that means that there's not really one standard that gives us the overlays that we want inside of SDN as well. Okay. And they're normally tied to the vendor's hypervisor as well. And that means policies that we apply, okay, a lot of times, okay, cannot be applied between different VMs and different hypervisors. So you might be running Hyper-V on one particular server. You might be running ESXi on another server. You might have a policy that applies in SDN that works insanely well with ESXi, but it may not work completely well with Hyper-V. Okay, so those are some of the idea of some of the limitations that ACI actually helps us to overcome as well. SDN is also still grounded and limited to network components. Okay, and that's the key as well. Whereas ACI is not limited in that way. Its limitation is due to the programming language they're actually running in the background. Okay, so if there's anything, that's what happens here. So even though SDN actually causes us to rethink the idea of networking, it is focused on the idea here, right? That we're really just getting things done quicker, whereas ACI though actually has differences here, okay, in what they do. So Vaughn, we still need both. Okay, we still need the ability to configure and do what we need to, but we also need that performance that SDN did for us. Okay, so how is it that ACI accomplishes this? Well, the first thing that they do in accomplishing this, Vaughn, is by changing the way that we do infrastructure itself, okay, in our model of thinking what we want to talk about, okay? So Vaughn, let's take a look at my screen, and this will help, at least I think it will help. We'll kind of take a look at this, okay? So we're on the left-hand side. This is our traditional type of what we call campus network, okay? And in the campus network, when we did something like this, we, of course, have servers that we might access. And if we had other things that we wanted to access as well, they would be located off of these access switches too. And here, the way that we normally do a traditional data center model in this way, right, is that all the access from access layer clients, like people on PCs, on laptops, on whatever they're actually trying to access in terms of these servers over here, well, they're on the other end of this, right? They're on access layer switches as well. They go through the core that makes everything faster, and that actually passes down and gets aggregated here at this distribution layer and the core layer up here too. Now, Vaughn, what we see in the traditional model, though, is that there's no guarantee here about how these links are actually kind of done. And what I mean by that, Vaughn, is that these could be single links if I wanted them to, just like down here, okay? But they also could be dual links too, okay? So like here, we have every single access layer switch directly connected to our distribution layer, okay? So that's actually a great benefit. But up here between the distribution and the core layer, notice again, we now have that full mesh topology here, okay? And this allows us to get away and do a lot of things differently, okay? Now, Vaughn, in between this, usually at this layer, they might actually be slower connections as well. So, Vaughn, if this is a gigabit connection here, let's say from here to here, and this also is a gigabit connection as well, let's say that the core, let's say that it jumps up to, let's do 10 gigabits here, okay? Well, that still means that there's a potential bottleneck when it aggregates traffic right through here, okay? And that's because what? These are gigabit links. Now, I'm not saying you can't change that, but what I'm saying is that if you do, you have to actually go ahead and change everything about how all those are connected. Sometimes even your access layer switches, though, Vaughn, they may not have 10 gig network cards in them to allow you to do that. So it just depends on what's happening. So the way that ACI actually says that things should be kind of structured in terms of a topology is more what they consider the idea of the spine leaf topology. These devices themselves, they can be identical devices. They're not actually two different, models. You can do that. But so let's take, for an example, like the ones that we're talking about here. We're going to use the Nexus 7000 as an example here, okay? So, Vaughn, I didn't actually have a particular icon on my drawing tool here on simple diagrams to kind of be able to show you the difference between a Nexus switch and a non-Nexus switch. So I had to make my own. So it normally has something like a star pattern on the front of it when you see this.
Did you make that?
I did.
You made that star from like little lines and everything?
Yeah, I
Good
did.
job,
Yeah,
Ronnie.
so that's what I did. Yep.
Not bad.
So there you go. Now I got lazy up here at the top. You can see where I actually just kind of drew. I'm like, forget it, I'm done. So I just made 2 triangles and yeah.
But it's still a visual reference that the triangles or the hourglass, is that what you were calling them?
Yeah, hourglass, something like that.
And
but
the arrows, so
yeah.
they can be different.
They can be different, yeah. But here, we're just going to say that they're the same. Now, Vaughn, when we implement something like this is kind of neat in the way that ACI data centers work, okay? We still have the same type of connection here. Notice I still have servers, but everything essentially is connected to leaves here, okay, when we do stuff. And notice this about the way that the topology works. Every leaf is directly connected to every spine switch that we have, okay? So notice that every single one is directly connected in that way. And that is a requirement. So it's not just, can I? Yes. Should I? Yes. Do I have to? Yes. Okay, that's the key, okay, is that it's actually designed this way. So notice that the spines, though, they're not directly connected to each other, nor are the leaves directly connected to each other either, okay? So in that sense, right, we only have direct connections up to the spine network here. And this 2-layer idea actually helps us out in terms of speed because of all the things that have to actually think about, okay? So we're going to take a look at this idea of the traditional model here just briefly, okay, and try and show you why this actually has limitations. So Vaughn, let's take for an example that each one of these switches here, okay, they have 32 ports together, right? But notice that each switch essentially is connected to those switches as well. So when we talk about the idea of how many ports are then available, okay, for extra devices to be plugged in. So if I need to add in another switch, well, how many additional ports are there available for me? Well, I have to think about the devices that I don't have, that I'm not actually doing the same thing to. So in other words, these links up here in the core. So there's 1, there's 2, there's 3, and there's 4, okay? Now all together, because this acts as a single unit, well, that would be 32 ports altogether, and let's say we'll subtract out 4, okay, for those links. When we do that, that limits it down to 28, right? Okay, right away. So Vaughn, with all these connections and the way that we have them connected, we go, all right, so I have a max of 28 different ports that I should be able to access at this point, all right, for additional aggregation if I need to. Now, Vaughn, what if the requirement changes up, okay? So let's take this example instead. So now, how many ports are available for access layer aggregation after doubling the number of uplinks, okay? Uplinks are the links in between switches, okay, is what we have. So Vaughn, if I had already reduced this down to 28 ports originally, and I now make sure that every single link that I originally had is doubled, that now takes up every single switch, has additional 4 ports into them, you got to realize something that now all of a sudden, in terms of access layer switches being able to do this, that literally cut it into 14 additional switches. So I went from 28 to 14. Yeah, I cut it in half, okay? Because I doubled what? The amount of connections that I had. So that means that, hey, if there were 28 before and I just doubled those connections, now there's only 14 that's left, okay? So that's something that you got to kind of pay attention to when you figure this stuff out, okay? Now, this is not so important for the exam in terms of you knowing those exact numbers, but it's knowing that the traditional model itself, there's limitations this way, okay? So Vaughn, as I continue to add in more and more switches, okay, down here, it also means I have to actually continue to add in more and more of this distribution layer or aggregation layer, depending on how you want to call it here, to make sure that everything works in the way that it needs to, okay? Now, with that though, Vaughn, okay, we change this too. So now there's a particular problem also, okay? So notice that we have, it says, when the world is associated with the topology above, what issue, okay? Well, the issue that we have is that after a while, we don't have scalability anymore, Vaughn, okay? So let's take a look just at the idea of the routers just for a moment. Now, Vaughn, you can buy these routers that have expansion ports to them and add in additional ports to make something like this happen. But just by default, Vaughn, there's 1, 2, 3, 4, 5 ports here for router interfaces just going to my data center if I do this, okay? Well, most routers might have 2, might have 3 ports just by default. So every time I add an extra device, Vaughn, if I add in another device over here, okay, that starts increasing the number of links then that everything has to actually, get access to as well, which then reduces the number of ports at the distribution layer, which then reduces the possibility of me adding in more and more devices down here. So that's why we have to actually think about this stuff. So there is a limitation in terms of scalability at this layer. So how does the spine leaf topology help? Well, this is what the spine leaf topology does instead, Vaughn. Okay? In the spine leaf topology, what they said is, here's the way it's going to be structured, Vaughn, so that you don't have to guess. So that we get super high speeds to our servers. These links in between are endpoint devices, okay, and our leaf devices, or leaves if we want to, those will always be 10 gigabit connections, okay? That's really fast type of connections. But that's not enough. So Vaughn, in north-south traffic, that's 10 gigabits of speed. But now between the leaf and the spine, that's considered east-west traffic as well, at a minimum is 40 gigs. You can also see usually up to 100 gig connections all the way in between. So Vaughn, we've essentially increased the east-west traffic here by going to 40 gigabit links or 100 gigabit links, which now means that I can continue to add in what? Multiple servers till I fill up the entire, all the ports on this leaf device if I want to. And more than likely, it's probably not going to overwhelm any of these connections up here in terms of this, okay? So this has benefits in this way, Vaughn. I can continue to scale out the number of devices that I want. And what that does is gives me the ability to continue to add in devices. And I really don't have to change the underlying infrastructure too much, okay? It also lets me know that I have pretty good bandwidth in between my leaf and my spine. I don't experience a lot of latency in here too, okay? Now over here on the right-hand side, Vaughn, if I want to say, hey, we want to connect out my data center out to a WAN or to layer 3 and out to the internet, we don't add in additional spine devices, okay? What we do is we add in additional leaves is what we do, and now those are called border leaves is what we actually call them. So to make all this work, Vaughn, the ACI fabric itself runs 3 different technologies to help us, okay? I would make sure I know them. Just kind of, not for any real purpose, Vaughn, but just make sure you know them, okay? One, of course, is at layer 3. It is using a routing protocol called is, okay? Intermediate system to intermediate system, okay? So those of us that are familiar with things like OSPF, we're familiar with the idea of the algorithm because it runs the idea of the shortest path first algorithm. But here in the spine leaf, this is the actual algorithm or the routing protocol that it uses, which is ISIS, which we don't tend to see on Cisco exams anymore, except for this one, okay? At layer 2, it is doing a VXLAN overlay, okay? And that means, remember, we're not actually taking a look under the hood, how all this stuff is working. We're trusting that it's actually working. And then for control N, it's actually using multi-protocol BGP, okay? Sometimes abbreviated as MP-BGP as well. I wrote it out because I didn't remember if I could actually remember what MP stood for. That's why I wrote it down, okay? So Vaughn, this is actually great in what we want to be able to do and understand. Now, once we have that understanding here, okay, I want to actually kind of show you a couple of different things and why this is important too, okay? So Vaughn, once we get that understanding, here's what we have to pay attention to in terms of scenarios, okay, that we might consider if we're actually having to do a build case of some sort, okay? So Vaughn, in a spine leaf topology, okay, what I'm told is I need to increase the bandwidth available to servers, okay, being able to get access out, being able to go across the WAN, being able to communicate with other devices here, okay? Well, the way that I do that is not by building out the entirety of everything, okay? Vaughn, I simply add in additional spines. And I made the different colors here so that you could see. So before, if you take all the black links, right, all together, okay, you can add all that bandwidth up together and go, all right, here's my total bandwidth that I have access to. But Vaughn, notice by simply adding in additional spine switches, you actually add up all across there. And now if each one of them, let's say, is 100 gigs, that's insane, but just kind of think about it that way, right? You get double the amount of bandwidth by me simply doubling the spines up here, okay? Notice I didn't have to increase anything else. I just doubled the spine, okay, is all I did. So if I'm actually needing to scale bandwidth, I add additional spine, okay, switches is what I do. And all this technology works at layer 2. But if I need to add in additional ports so that I can support more and more host devices for virtual machine hosts that are out there, well, I just add in additional leaves instead. So because this is so much of a faster bandwidth connection by comparison, we don't really have to expand a lot. But you come to a point where you do have to expand, but just kind of realize that this is the way it works. Notice that our border leaves here, once again, we're not having to change the entire hierarchy once again to make this all work. We just add in our leaves, and we just make sure that those leaves are connected to every single spine. And now, Vaughn, between every single one of these, right? So between this particular switch and out to the internet, notice it's really 1 and 2 hops here, okay? It doesn't matter where you're located across the spine. If you're actually on this one, you actually go 1, and then 2, you're out, okay? So it actually makes it a very stable and very deterministic type of networking that we're able to do with the spine leaf as well, okay? So ACI technology is actually designed to help us to understand that and do that as well, okay? Now, Vaughn, we still need to talk a little bit more about what it really does, but then I want to show you, of course, a demonstration on how the ACI actually works effectively across multiple devices, and also introduce you to some of the terminology in a real world type of scenario that you do see here. Okay, so Vaughn, let's go ahead and do this. We'll actually pick up on a part 2, and we'll finish this out, and that way we'll have a good understanding of how ACI actually works, and even see how it's actually going to work in the working. Yep.
In the working.
That's right.
Yes, how it's going to work in the working. You heard the man. That sounds like a good idea for more valuable information. So thank you so much for joining us, but we're going to go ahead and sign off for IT Pro TV. I've been your host, Vaughn Smith.
And I'm Ronnie Wong.
We'll see you soon.
Thank you for watching IT Pro TV.